Swayam Prabha. Digital India. Educated India.
Yeah. Now, in connection with we discussed the regression line. Some more theory we are going to discuss, and it will be very helpful in machine learning and artificial intelligence. So, this is most required analysis. Let us start with linear regression. So, regression is a fundamental problem in machine learning, and a regression problem appear in diverse range of the research areas and applications, including time series analysis, example system identification, control and robotics, example reinforcement learning, and forward and inverse model learning, and also optimization like line searches, global optimization, and deep learning application like computer games, speech to text translation, image recognitions, automatic video annotation. So, regression is also a key ingredient of classification algorithm. Finding the regression function requires solving a variety of problems, including the following. Number 1, a data set, and number 2, possible solution to the regression problem. That is, A stands for the observed noisy function values from which we wish to infer the underlying function that generated the data, and B picture represent the possible function that could have generated the data, because joining all the points we have a function could have a generated data. The blue curve indicates the measurement of the noise of the function value corresponding input, and orange is distribution. So, this is the picture demonstrated with the data set and a possible regression line. Now, the choice of the model and the parameterization of the regression function. Given a data set, what function classes, example polynomials, are good candidates for modeling the data, and what particular parameterization, that is degrees of the polynomial, should we choose. Model selection, as discussed in the section, allow us to compare the various models to find the simplest model that explain the training data reasonably well. Finding good parameters, having chosen a model of the regression function. How do we find a good model parameters? Here we will need to look at different laws or objective functions. They determine what a good fit is and optimize the algorithm that allow us to minimize these loss. And next one is overfitting and model selection. Overfitting is a problem when the regression function fits the training data too well, but does not generalize to unseen data set. Overfitting typically occurs if the underlying model is overly flexible and expressive. So, we will look at the underlying reasons and discuss ways to mitigate the effect of outfitting in the context of linear regression. So, the relationship between the loss function parameter priors. So, the loss function is optimization objectives are often motivated and induced by a probabilistic model. So, we will look at the connection between the loss function and underlying prior assumption that induce these losses. Next, uncertainty model. In any practical setting, we have access to only a finite potentially large amount of data for selecting the model class and corresponding parameters. Given that this finite amount of training data does not cover all possible scenarios, we may want to describe the remaining parameter uncertainty to obtain a measure of confidence of model's prediction at test time. The smaller the training set, the more important uncertainty modeling. Consistent modeling of uncertainty equips model prediction with the confidence bounds. Now, we are going to discuss the formulation of the problem. Because of the presence observation noise, we will adopt a probabilistic approach and explicitly model the noise using a likelihood function. More specifically, throughout this chapter or this talk, we consider a regression problem with the likelihood function p of y bar x equal to n of y by f of x comma sigma square. Here x in r power d and are inputs and y in r are noisy function values, and targets with the equation 9.1, the function relationship between x and y is given by y equal to f of x plus epsilon, where epsilon belongs to n of 0 comma sigma square is independent and it is identically distributed. Gaussian measurement noise with the mean 0 and variance sigma square. So, our objective is to find the function that is close to the unknown function f that generated data and that generalize well data. For the time being, we assume that the noise variance sigma square is known and focus on learning the model parameter theta. In linear regression, we consider a special case that the parameters theta appear linearly in our model. An example, the linear regression is given by p of y bar x comma theta equal to n of y bar x transpose theta comma sigma square. If and only if y equal to x transpose theta plus epsilon, where epsilon belongs to n of 0 comma sigma square, where theta in r power d are the parameters we seek. So, the class of function described are a straight line that passes through the origin. In the equation 9.4, we choose a parameterize f of x equal to x power t into theta. So, the likelihood in 9.3 is a probability density function of y evaluated at x power transpose of theta. Note that only source of uncertainty originates from the observation noise. Without observation noise, the relationship between x and y would be deterministic and would be a Dirac delta. So, the figure 9.1 says that the linear regression with the examples of a lot of straight line that can be described as the linear model. Here x comma theta in R, the linear regression model in 9.4 describes the straight line and the parameter theta is the slope of the line. The figure 9.2a shows some example functions for different values of theta. So, the B stands for the training set and C stands for maximum likelihood estimate. So, in the following we will discuss how to find the optimal parameter theta star belongs to RD for the linear regression of the model of 9.4. Once the parameter theta star are found, we can predict the function values of by using this parameter estimate, so that at an arbitrary test input x star, the distribution of corresponding target y star is p of y star by x star of theta star equal to n of y star by x star transpose theta star equal to sigma square. Now, maximum likelihood estimation. A widely used approach to finding the desired parameter theta suffix ml is the maximum likelihood estimation, where we find the parameter theta suffix ml that maximize the likelihood. And intuitively, maximizing likelihood means maximizing the predictive distribution of the training data given the model parameters. So, we obtain maximum likelihood parameter as theta suffix ml belongs to argument of maximum of p of y such that x comma theta. So, we have a note. So, the likelihood p of y by x comma theta is not a probability distribution in theta, it is simply the function of parameter theta, but does not integrate to 1 and may not even be integrable with respect to theta. However, the likelihood 9.7 is a normalized probability distribution in y. So, to find the desired parameter theta suffix ml that maximize the likelihood, so we typically perform the gradient ascent or gradient descent on the negative likelihood. In the case of linear regression, we consider here, however, a closed form solution exists, which makes the iterative gradient descent unnecessary. In practice, instead of maximizing the likelihood directly, we applied the log transformation to the likelihood function and minimize the negative log likelihood. So, we have a note on log transformation. Since the likelihood of 9.5b is a product of n Gaussian distribution, so the log transformation is useful since it does not suffer from numerical underflow. And second point, the differentiation rule will turn out simpler. More specifically, the numerical underflow will be problem when we multiply n probabilities, where n is the number of data points, since we cannot represent very small numbers such as 10 power minus 256. Furthermore, the log transformation will turn the product into a sum of log probabilities such that the corresponding gradient is a sum of the individual gradients instead of a repeated application of the product rule to compute the gradient of the product of n terms. So, to find the optimal parameter of our linear regression problem, we minimize the negative log likelihood of minus of log of p of y bar x comma theta equal to minus log of product of n equal to 1 to n p of yn by xn comma theta equal to minus summation n equal to 1 to n log of p of yn by xn comma theta. So, we exploited that the likelihood and factorize over the number of data points due to our independence assumption on the training set. So, in the linear regression model, the likelihood is a Gaussian due to Gaussian additive noise term such that we arrive at a log of p yn by xn comma theta equal to minus 1 by sigma square into yn minus xn transpose theta the whole square plus constant. So, where constant includes all the terms independent of theta, and equation 9.9 is a negative likelihood. So, we obtain the ignoring the constant terms L of theta equal to 1 by 2 sigma square summation n equal to 1 to n yn minus x1 t theta whole square. So, 1 by 2 sigma square into y minus x theta the whole transpose into y minus x theta, when x bar equal to norm of y minus x theta square by 2 sigma square. So, we can correlate in terms of this function to the norm of the function. So, where we define the design matrix x equal to x1, x2, xn as a collection of training input, and y equal to y1, y2, yn belongs to R power n as a vector that collects all the training targets. Note that nth row of the design matrix corresponding the input xn in the equation 9, 1, 10b. So, we have now a concrete form of the negative likelihood function we need to optimize. So, we immediately see that 10b is a quadratic in theta. This means that we can find the unique global solution theta suffix ml for minimizing the negative likelihood L. So, we can find the global optimum by computing the gradient L, setting it to 0 and solving for theta. So, using this result from the chapter, we compute that the gradient L with differentiate with respect to theta, then we have d by d theta of 1 by 2 sigma square of y minus x theta t y minus y x theta. Now, 1 by 2 sigma square is constant, take it outside, and d by d theta of product term y y transpose minus 2 y transpose into x theta plus theta transpose x transpose x theta will come. Right? And then further differentiate with respect to theta, first term becomes 0 and second term is y transpose x and theta transpose x, and 2 take it outside, get cancelled. So, we have 1 by sigma square is minus y transpose x plus theta transpose x transpose x into this, which belongs to r power 1 cross d. So, the maximum likelihood estimated is theta ml solves dl by d theta equal to 0 transpose necessary optimum. Therefore, if this is equivalent to 0, if and only if the equation 9.11c equal to 0, therefore, theta ml transpose x equal to y transpose x. Therefore, theta ml transpose equal to y transpose x into x transpose x of whole inverse. Therefore, theta ml equal to x transpose x whole inverse into x transpose y. So, we could multiply the first equation by x transpose x whole transpose, because x transpose x is a positive definite if rank of x equal to d, where rank of x denotes the rank of x. Note, setting gradient to 0 is a necessary and sufficient condition. So, we obtain the global minimum since the Hessian function delta square theta of L of theta equal to x transpose x belongs to r power d cross t is a positive definite. Note, the maximum likelihood in the solution of 9.12c requires to solve a system of a linear equation of the form a theta equal to b and a equal to x transpose x and b equal to x transpose y. So, example fitting lines, let us have a look at in the figure 9.2. Have a look at the point 9.2, right, where we aim at the fit straight line f of x equal to theta x, where theta is unknown slope to a data set using maximum likelihood estimation. So, example of function in this model class straight line are shown in the figure for the data set. So, we find the maximum likelihood estimate the slope of the parameter theta, obtain the maximum likelihood. So, the maximum likelihood estimate with the features. So far we consider a linear regression setting described in 9.4, which allowed us to fit straight line to data using maximum likelihood estimation. However, the straight lines are not sufficient expressive when it comes to fitting more interesting data. Fortunately, linear regression offers us a way to fit nonlinear function within the linear regression framework. Since linear regression is only refers to linear in the parameters. So, we can perform an arbitrary nonlinear transformation phi of x of the input x and the linearly combine the components of this transformation. So, the corresponding linear regression model is p of y by x comma theta equal to n of y by phi transpose of x into theta comma sigma square, if and only if y equal to phi transpose of x into theta plus epsilon, which is equal to summation k equal to 0 to k minus 1 theta k into phi of k x plus epsilon, where phi is such that r power d maps to r power k is a nonlinear transformation of the input x, and phi k is such that r power d to r is the kth component of the futures vector phi. Note that the model parameter theta still appear only linearly. Next example, we have a polynomial regression. So, we are concerned with the regression problem y equal to phi transpose of x into theta plus epsilon, where x in R and theta in R power k. So, the transformation that is often used in the context is phi of x equal to phi naught of x, phi 1 of x and so on, phi k minus 1 of x is 1 x, x square, x cube and so on, x per k minus 1 belongs to R per k. So, this means that we lift the original one dimensional input space into k dimensional future space consisting of all monomials x per k in for k equal to 0 to k minus 1. With these futures, we can model the polynomials of degrees less than or equal to k minus 1 within the framework of linear regression. The polynomial of degree k minus 1 is f of x equal to summation k equal to 0 to k minus 1 phi theta k into x power k equal to phi transpose of x into theta, where phi is defined as in the equation 9.414 and theta is theta 0 into theta k minus 1 transpose belongs to R power k contains the parameter theta k. And let us now have a look at the maximum likelihood estimation of parameter theta in the linear regression model. So, we consider the training input x in R power d and the targets yn in R and n varies from 1 to n, and define the future matrix is phi equal to phi transpose x1 to phi transpose xn, which is equal to phi naught of x1 and so on phi k minus 1 of x1. So, phi naught of x2 to phi k minus 1 of x2 and phi naught of xn to phi k minus 1 of xn belongs to R power nk, n cross k, where phi I j equal to phi j of xi and phi j is Rd maps to R. Now, we are going to discuss one example, the future matrix for second order polynomial. For second order polynomial, n training points xn in R, so n varies from 1 to n. So, the future matrix is phi equal to 1 x1 x1 square, 1 x2 x2 square and so on 1 xn xn square, and with the future matrix phi defined in 9.16, the negative log likelihood for the linear regression model 9.13 can be written as log of p of y over x comma theta equal to 1 by 2 sigma square of y minus phi theta whole transpose into y minus phi theta plus constant. So, comparing 9.8 with the negatively log likelihood in 9.10b for the future free model. So, we immediately we see we just you need to replace x and phi. Since both x and phi are independent of the parameter theta, so we wish to optimize. We arrive immediately at the maximum likelihood estimate theta ml equal to phi transpose phi whole inverse into phi transpose y for the linear regression problem with the nonlinear futures defined in 9.13. So, we have a note, when we were working without features, we required x transpose x to be invertible, which is the case when rank of x equal to d. So, the column of x are linearly independent. In 9.919 we therefore require phi transpose phi belongs to R power k cross k to be invertible. So, this is the case only if R of phi equal to k. So, we have a maximum likelihood polynomial fit based on regression data set and a polynomial of degree 4 determined by maximum likelihood estimation. So, in the figure A consisting of what xn to yn pair where n varies from 1 to 10. So, we have a point data set in MLP, and for the second picture shows that the polynomial of degree 4 for MLP, and that is estimated, and the blue line stands for MLE and plus is the training data. So, based on this figure A, here n equal to 10 and the xn varies from -5 to 5 the interval. Therefore, it forms the sine as well as cos sinusoidal wave associated s minus Sn of xn by 5 plus cos of xn plus epsilon, where n belongs to where epsilon belongs to n of 0 comma 0.2 square. So, we fit the polynomial of degree 4 using maximum likelihood estimation with parameter theta suffix ml are given. So, the maximum likelihood estimate yields the function phi power t of x star of theta ml at any test location. So, this result shows the figure B,